Welcome to the deep dive. Today we're going deep, literally to explore electrical submersible pumps, or ESPs for short. You submitted a university lecture on them, so it seems you're pretty interested in how these things get oil flowing from way underground.
That's right. ESPs are essential in oil production. They're basically pumps submerged in the oil using a motor to push it upwards.
Okay, so we know they're important, but the lecture gets pretty technical. What are some of the key takeaways that someone in the oil industry should really grasp?
Well, one of the most fascinating aspects is how ESPs convert energy. They take that rotary energy from the motor and transform it into kinetic energy, which then becomes pressure energy to force the oil up.
So it's like a chain reaction of energy all happening within this pump deep underground.
Exactly. And understanding that chain reaction helps us appreciate the role of the key components, the impeller and the diffuser.
Right, those terms came up a lot in the lecture. Could you break those down for us?
Sure. The impeller is the part that spins pushing the oil outwards. You can think of it like a fan blade. But then the diffuser, which is stationary, slows down that fast-moving oil and converts that velocity into pressure.
Clever. So it's not just about moving the oil, it's about building up the pressure to push it thousands of feet upwards.
Precisely. And to achieve that incredible lift, ESPs use multiple stages, each with its own impeller and diffuser set. These stages are stacked, and as the oil goes through each stage, the pressure increases.
That makes sense, but how do engineers figure out how many stages an ESP needs? It must depend on how deep the well is and how much oil they need to pump.
You're absolutely right. That's where the pump characteristic curve comes in. It's essentially a graph that shows how the pump performs under different conditions, kind of like a fingerprint for that specific pump design.
A fingerprint, that's an interesting way to think about it. So what can we learn from this fingerprint?
It shows the relationship between the pump's head, or how high it can lift the fluid, and the flow rate, or how much fluid it can move per unit of time.
Okay, so it's a visual representation of how much the pump can lift versus how much it can move at any given time. That must be crucial when you're designing a system for a specific well.
Exactly. The lecture gives a great example of lifting oil 2,000 feet at a specific flow rate. By analyzing the characteristic curve for a single stage, engineers can calculate exactly how many stages are needed to achieve that lift.
Let's dive into that example a bit. What are some of the steps involved in that calculation?
First, they look at the performance curve for a single stage of the pump. Let's say for this example, each stage can lift the oil 40 feet.
Okay, so each stage gives you a 40-foot boost. Then what?
Then they divide the total lift required, in this case 2,000 feet, by the lift per stage, which is 40 feet. That tells them how many stages are needed for the entire system.
So 2,000 feet divided by 40 feet per stage. That's 50 stages. It sounds simple when you break it down like that, but I imagine there's a lot more to consider in a real-world scenario.
There are certainly a lot more complexities, but understanding this basic calculation is a great foundation.
Absolutely. We've covered the basic workings of ESPs and how engineers figure out how many stages are needed. Where do we go from here?
Well, the lecture also touches on the concept of the best efficiency point, or BEP. This is a crucial factor in optimizing ESP performance and ensuring the system operates as efficiently as possible.
That sounds like a fascinating topic. I'm eager to learn more about how engineers find that sweet spot for efficiency.
Let's take a deeper dive into the BEP in part 2.
Welcome back to the deep dive. We're picking up where we left off, ready to explore that intriguing concept of the best efficiency point, or BEP.
Yeah, the BEP, it's a key factor in understanding how to get the most out of these powerful pumps.
Right. You mentioned that it's all about finding that sweet spot where the pump operates most efficiently. But why is this BEP so important in the grand scheme of things? What are the real-world implications?
Well, imagine you're running a marathon. You wouldn't sprint at the start, would you? You'd pace yourself to conserve energy and perform your best throughout the race.
Okay, I see where you're going with this. So the BEP is all about finding that optimal pace for the ESP, ensuring it runs efficiently and reliably over the long haul.
Exactly. And these ESPs often operate thousands of feet underground in harsh conditions and need to run continuously for years, even decades.
So finding the BEP isn't just about saving energy, it's about maximizing the lifespan of these expensive pieces of equipment.
Precisely. Operating at the BEP minimizes wear and tear, reducing maintenance costs and extending its lifespan. It's a win-win situation.
That makes a lot of sense. But how do engineers actually determine the BEP for a specific ESP? Is it a complex calculation?
It's not magic, but there's definitely some science involved. Remember that pump characteristic curve we talked about earlier?
The one that shows the relationship between head and flow rate?
That's the one. The BEP is typically found near the top of that curve, where the head is highest for a given flow rate.
So if we visualize the curve, the BEP is like the peak of a mountain.
You got it. Engineers use sophisticated software and calculations to pinpoint that exact spot on the curve. But it's not just about finding the BEP on paper, it's about making sure the ESP actually operates at that point down in the well.
That sounds like a challenge. How do they make that happen?
It involves a lot of careful planning and adjustment. They need to select the right motor size for the ESP and then control the pump speed and flow rate to match the well conditions.
So it's not a set it and forget it kind of system.
Yeah.
It's a dynamic process that requires ongoing monitoring and adjustment.
Absolutely. Think of it like fine-tuning an instrument. You need to make small adjustments to get the perfect sound.
I'm starting to appreciate the complexity involved here. It's not just about plugging in a pump and letting it run.
Right. And finding that BEP is crucial because when an ESP operates at that sweet spot, there are so many benefits.
Like what?
Well, we've already discussed the improved energy efficiency and the extended lifespan, but it goes beyond that. Operating at the BEP also minimizes vibration and noise, which can be a big problem in those deep, confined well environments.
I bet that's a relief for anyone working near these wells. Less noise and vibration means a safer and more comfortable work environment.
Exactly. Plus, minimizing vibrations reduces stress on the equipment, leading to fewer breakdowns and repairs. It all adds up to a smoother, more cost-effective operation.
This has been an eye-opening deep dive into the importance of the BEP. It's clear that finding that sweet spot is crucial for maximizing efficiency, extending the life of the equipment, and ultimately boosting oil production. But I have a feeling there's more to this story, right?
There's always more to explore. In our final segment, we'll shift gears and look at some of the real-world challenges that ESPs face down in the well. Remember, all these concepts we've discussed so far are happening in a pretty extreme environment.
That sounds intriguing.
Yeah.
I'm eager to learn how those theoretical concepts we've discussed translate into practical applications and what engineers are doing to overcome those challenges.
Let's dive into that in part 3.
Welcome back to the deep dive. We've covered a lot of ground on ESPs, from the basics of how they work to that crucial concept of the BEP. Now, I'm really curious about those real-world challenges you mentioned. What kind of curveballs does nature throw at these pumps down in the well?
Well, think about the environment these ESP operate in. Thousands of feet underground, extreme temperatures, and often surrounded by corrosive fluids. It's a tough job.
So it's not just about finding the perfect pump on paper. It's about choosing one that can withstand a beating right. What are some of the key factors engineers have to consider when it comes to material selection?
Oh yeah, material selection is absolutely critical. You need metals that can handle the heat, the pressure, and the corrosive fluids. Some wells are highly acidic, others have a lot of salt, and that all eats away at the pump over time.
I imagine that adds a whole other layer of complexity to the design process. You're not just picking a pump off a shelf. You're essentially designing it for a specific environment.
Exactly. And then you've got sand and other solids that can cause erosion. It's like sandpaper constantly wearing down the pump components.
So it's a constant battle against corrosion and erosion just to keep the pump functioning. What are some of the ways engineers are tackling this challenge?
Well, one approach is to use more robust materials like high-grade stainless steel or even special alloys designed for extreme environments.
So it's about using tougher materials, but I imagine that comes with a higher price tag.
There's always a trade-off between cost and durability. Sometimes it's worth investing in a more expensive material if it significantly extends the lifespan of the pump and reduces maintenance costs.
It's a long-term investment for sure. Are there any other tricks up their sleeves when it comes to combating wear and tear?
Another strategy is to design the pump in a way that minimizes erosion. For instance, they might create smoother flow paths to reduce the impact of those abrasive particles. It's all about understanding fluid dynamics and how to minimize the wear points.
That's fascinating. It's like they're using design to outsmart the harsh environment.
Exactly. But it's not just about solids causing problems. We also have to deal with gas in many oil wells.
Right, you mentioned that earlier. Why is gas a problem for ESPs?
Imagine trying to drink a milkshake through a straw with a hole in it. You're not going to get much of a milkshake, are you?
That's a great analogy. So the gas is essentially disrupting the pump's suction, making it less efficient.
Exactly. In some cases, too much gas can even cause the pump to lose prime completely, meaning It stops pumping altogether. That's a big problem.
So what's the solution? Do they just try to keep gas out of the pump entirely?
Well, that's one approach. They use gas separators, which are devices that separate the gas from the oil before it enters the pump. It's kind of like a filter for gas.
Okay, that makes sense. But I imagine that's not always 100% effective. What happens when gas does get into the pump?
That's when you need a more specialized system. Some ESPs are designed with built-in gas handling capabilities. They might have a special intake design that allows gas to pass through without disrupting the flow of oil, or they might use a different type of impeller that's less sensitive to gas interference.
So it's like they're designing pumps that can handle a bit of gas without getting choked up.
Exactly. It's all about anticipating potential problems and engineering solutions that can keep those pumps running smoothly, even in the face of challenging conditions.
It's amazing how engineers are constantly innovating and coming up with new ways to optimize these systems.
And remember, it's not just about the pump itself. The entire ESP system, including the motor, the cables that power it, and the surface equipment that controls it all, has to be carefully designed and maintained.
So it's a truly holistic approach considering every aspect of the system from the bottom of the well to the surface.
Precisely. And of course, we can't forget about the cost factor. These ESP systems are complex and require specialized materials and engineering.
Right. We talked about the trade-off between cost and durability,
Yeah.
but I imagine the initial investment for one of these systems is pretty substantial.
It can be. And then you have the ongoing costs of maintenance repairs and eventually replacement.
So it's a constant balancing act for oil producers, weighing the benefits of increased oil production against the costs of operating and maintaining these sophisticated systems.
That's the reality of the industry. It's a high-stakes game where efficiency and reliability are paramount. Every barrel of oil produced has to justify the investment in the technology that makes it possible.
This deep dive has given me a whole new appreciation for the complexity of oil production. It's not just about drilling a hole and watching the oil flow. It's a delicate dance of engineering, technology, and economics.
It absolutely is. And we've only scratched the surface of ESPs. There's a whole universe of fascinating technologies involved in getting that oil out of the ground and to the refineries.
It's exciting to think about all the innovation happening in this field. But for now, let's bring it back to our listener. What are some key takeaways you'd like them to walk away with?
If you're interested in ESPs, this is just the beginning. There's a wealth of information out there. Delve deeper into different types of pumps, research the latest advancements in materials and gas handling, and explore the world of artificial lift technology.
And don't be afraid to get hands-on. Maybe even try building a model pump or experiment with different designs. Who knows, you might be the one to come up with the next breakthrough in ESP technology.
That's the beauty of learning. There's always something new to discover. So keep asking questions, keep exploring, and keep diving deep into the world around you.
Great advice. And for our listeners, if this deep dive sparked your curiosity, we encourage you to keep learning and exploring the fascinating world of ESPs and the technology that powers our modern world. Until next time, happy learning.